Part 2 discusses the classification of igneous rocks. So how do we tell different igneous rocks apart from one another? And what subgroups do we put them in to identify how they formed and specific characteristics they have? One of the main ways to do this is through determining whether an igneous rock is intrusive or extrusive. An intrusive igneous rock solidified underneath the ground from a melt, whereas an extrusive rock solidified above Earth's surface from a melt as well. So in the picture to the left, we have a magma chamber beneath the surface. We've got different pieces of magma coming up through the volcanic vent and exploding out of the top, where we have a lava flow. So that lava flow would be an extrusive igneous rock, whereas if the rocks cooled in the magma chamber beneath it or in the conduits beneath the surface, they would be intrusive. Ash flows also, and ash clouds, once they fell to the ground, would be extrusive. So in the rocks to the pictures to the right, which would you guess of the two is intrusive versus extrusive? You can pause your video now, think about it for a few minutes. The intrusive igneous rock is the top picture, and this is the reason we know this is that it's cutting through another igneous rock vertically, whereas the rocks below in the bottom picture are both extrusive. These are both lava flows deposited one on top of another. And so if you don't have a trained eye, it can be hard to tell sometimes whether a rock is intrusive or extrusive. But horizontal rocks on top of one another can be flows, so you have to keep that in mind. Let's provide some terminology for different types of intrusive igneous rocks. So dikes are igneous intrusive rocks that cut across existing layers or cut across existing rocks. So the top picture in the previous slide was a picture of a dike. And sills are igneous intrusive rocks that push between layers, so they are spreading out horizontally. So the picture on your left shows an example of a dike and a sill. These often occur together because the magma is always looking for a path of least resistance to flow. Sometimes it's horizontal, and sometimes it's vertical. Igneous intrusions on a larger scale are known as laccoliths, plutons, and batholiths, and these are all different sizes and shapes of large magma bodies beneath the surface that have accumulated and later cooled and solidified. So if you see large pieces of granite at any outcrop, or if you know that your house is built on a big granite body, then this formed from a pluton. This was once cooling underneath the ground, either as a pluton or a laccolith or a batholith. Extrusive igneous bodies can be classified either as lava flows or pyroclastic debris. So lava flows are not viscous, so they have low resistance to flow, and that means they can flow well. So viscosity of a lava is determined by both silica content and also temperature. Felsic lavas are highly viscous, meaning they don't flow well, and mafic lavas are have low viscosity, meaning they do flow well. This determines how far flows extend and the kind of structures they create. Pyroclastic debris is made up of solid fragments from eruptions that have either tumbled down the face of the volcano or been exploded into the air and fallen from the atmosphere. These debris are classified by size, with the smallest grain size being ash, and then going from glass and bombs are also the largest grain size. So on the bottom left corner, we've got some volcanic bombs, also known as blocks, with a human standing next to it for scale. And then in the top picture, we have some photomicrograph of volcanic ash with a scale bar. There are a few special types of lava flows. These are known as pahoehoe, a'a, and pillow basalts. Pahoehoe and a'a are Hawaiian words that are used to describe different basalt flows over the surface of land. So pahoehoe is a low volume lava that has soft, solid surfaces and develop rope-like ridges as they cool. So you can see the two rope-like textures in the left side photos. A'a is typically a larger lava flow that has a jagged and rubbly surface. Pillow basalts develop when lava erupts underwater and cools quickly as it interacts with the extremely relatively cold ocean or lake water. And so these picture below is of pillow basalts. Now let's classify igneous rocks in terms of their texture or grain size, just as we would with any other rock type. So the texture of igneous rocks can be crystalline, can be fragmental, or glassy. Crystalline rocks cooled slowly, whereas glassy rocks cooled very rapidly and were not allowed to minerals to form. Fragmental rocks are kind of an in-between type that were exploded out of a volcano and were rapidly welded or cemented together in a hot fluid-rich atmosphere after an explosion. In addition to texture, we need to understand the composition of igneous rocks to identify or classify them. Composition is the relative proportion of different elements and minerals in the rock. And even when composition is the same, different cooling rates result in different textures. For example, a fine versus a coarse rock of the same composition may be a basalt or a gabbro. Now, the basalt and gabbro are mafic rocks. This is true for ultramafic, intermediate, and felsic rocks as well. So many of us are familiar with granites. Those are coarse grained, meaning they cooled slowly underground. But the complement to the granites that is fine grained and cooled above the surface as a lava flow or a pyroclastic flow is known as a rhyolite. The figure on the bottom right shows the different relative mineral compositions for these rocks. As you go from mafic to felsic, you're increasing quartz content, you're decreasing pyroxene and olivine content. And this figure is related to the Bowen's reaction series. We can also classify igneous rocks by their eruption type. Effusive eruptions are low viscosity lavas that flow relatively easily. And a great example is a mafic eruption of basalt on the islands of Hawaii. Explosive eruptions are formed when high viscosity lava flows more slowly out of volcanoes. Pressure builds up and there becomes a high energy release that is the explosion. These are violent with blasts that distribute large amounts of ash and other pyroclastic material. One example is in Mount Etna of Italy, where this picture was taken. Volcanoes have a specific architecture that includes a magma chamber connected to the surface by a conduit, and lava erupts through either main conduits or vents or auxiliary conduits or vents or flank vents. The different types of volcanoes provide us some information on the composition of the magma beneath them. So shield volcanoes are broad, gentle domes composed primarily of mafic lava flows. These can build up to massive structures. For example, Mauna Loa is the largest shield volcano on Earth in Hawaii, and this is made of mafic lavas that have gently flowed out of the summit of Mauna Loa over a periods of thousands, millions of years. These tend to have effusive eruptions. Cinder cone volcanoes are symmetrical cone-shaped piles of cinders or ash with pit-like craters at their summits. These form from very short-lived effusive eruptions. Stratovolcanoes are large and cone-shaped with alternating layers of lava and pyroclastic materials, where lava flows in stratovolcanoes are mainly felsic. These are the typical volcanoes that you think of if you were to picture a volcano. And they're also known as composite volcanoes, and they have explosive, violent eruptions. Here we have a picture of Mount Fuji, which is a stratovolcano. Volcanic calderas form when the summits of volcanoes collapse into the drained magma chambers below. So there's nothing holding up the summit anymore. And these are usually circular or elliptical and can be up to tens of kilometers across and hundreds of meters deep with a flat floor. In part 3, we will discuss volcanic hazards and the plate tectonic context.